Thanks for tuning in to another episode of Free GMAT Prep Hour. Just a reminder, you've got some other options at your disposal, free options. Always welcome to sample one of our in-person or online classes. Just kind of come to the first session and see what the GMAT's all about, or see what Manhattan Prep courses are like. And there's also kind of a free option to trial out our interactive product, GMAT Interact, which has a bunch of kind of video lessons, a few dozen video lessons, and I think you can try out a few of those lessons, no strings attached too. So just go to this website that's on your screen right now. Check out more. We also are going to be doing more iterations of Free GMAT Prep Hour, continuing to do that. In fact, I think I'm scheduled to do one in a couple more weeks, like March 5th. Anyone have any topic suggestions? Always happy to hear some suggestions of what students want to look at. Maybe a verbal topic, if anyone has any verbal suggestions. Go ahead and let me know in the chat box. Today, I have determined that we are going to work on rate problems. And so I hear from a lot of tutoring students, just students in general, that on the quant side of things, rate problems involving distance, rate problems involving work done by machines, making widgets and things like that are a source of anxiety. So I'm going to talk with you about a handful of rate-related problems, not related rate problems, that's different, but rate-related problems with distance, distance traveled, and then work completed, and kind of talk about some of the best practices or strategies you can use for those types of problems. So you've got the chat box here. Please let me know if you have questions as we go, and if I'm asking for feedback, just kind of don't be shy. Hit me up in the chat room. Yes, another quick question that came in, which I think is valuable. We can talk about verbal questions in a future session. It's hard to talk about specific problems that aren't from free resources. So for copyright reasons, we can't just kind of bring in just any problem that's out there. But there are some free resources out there, and if the problem comes from a free resource like the 2 free practice official GMATs that are on NBA.com, if a question comes from there, and I'll have some of those today, we can talk about those in class. Someone suggesting reading comp and inferences. There's someone that's raised their hand. If you've got a question, just go ahead and type it in chat, and I will try to keep up with some of this stuff. But you can ask some specific, or if you want to look at specific GMAT questions, not all of them are fair game, and we do have to kind of play by the rules there. So if it's from a free resource, that's fair game. Cool. So I will be monitoring the chat box. Sorry for the people at home watching this on a recording. You don't get to see the chat box, but I will try to do my best and say the problems or the questions that are coming in through chat. Cool. Let's get started. Rates. First, we're going to talk about rates as they relate to distance. Now, I'm sure a lot of people out there recognize that when you see a rate problem related to distance, you're supposed to think about this equation. Distance traveled is the product of the rate or the speed of the travel multiplied by how long it takes to travel, right? Or distance equals rate times time, or D equals RT. Good. And we need to know this equation, but we also have to understand how the elements relate to one another. So we're going to talk a little bit about that, and then I'll throw you into some questions. Let's just take a look at this quick sample question. Take a moment and think about this. Don't type your answer into chat yet, though. Okay, so I think that's enough time. to think through this problem. Let's go ahead and work it out. And you might notice that we can't just kind of situate the 40 for the distance and the 30 minutes for the time, or excuse me, 40 for the rate and 30 for the time, and just get the product of the distance. Because if you're trying to put that into this equation, d equals RT, and we throw 30 minutes in for time, and we throw 40 minutes in for the rate, all of a sudden it pops out as 1,200 for the distance. And common sense should tell you that you've gone far too far. No way did you go 1,200 kilometers. And so what we need to make sure of when we're dealing with distance, rate, time problems is that you're minding your units, okay? So one of these units is given as kilometers per hour. And the other one, the time, is not given in hours, it's given in minutes. So we're gonna have to make sure that we get our units aligned and convert 30 minutes to hours, or half of an hour. And now it should make more sense. So instead of 30 minutes, we're gonna have half of an hour. And now the units should work out. And we're just down to 20 kilometers. So if I clean that up a little bit, what's actually happening here, and I know a lot of people just see 30 minutes and immediately convert that to half an hour, but what we can do is, to make sure we're more systematic about this when the unit conversions get a little bit tougher, and I think they will in a few minutes, I know they will, is we can take 40 kilometers per hour as a rate and multiply it by our time of 30 minutes. But we see that the denominator's time unit does not match up with the numerator's time unit. And so what we need to do is make sure that those time units kind of end up working out. And so the conversion here is that 1 hour is equal to 60 minutes. And now we have hours in both the numerator and the denominator. We have minutes in both the numerator and the denominator. And now we're seeing we're going to multiply 40 by 30 over 60, which is that 1/2 an hour we came up with earlier. So setting up the unit conversions is really, really critical here, just to make sure you know how to do it. Now 40 times 30 divided by 60, the only unit that's left is kilometers. We can do some canceling out here. 40 divided by 2 is 20 kilometers, which is probably what you all ended up with. But it's key to understand how to mind your units on easier problems before you start kind of ratcheting things up to harder problems. So watch out for your units in these types of problems. Cool. Let's take a look at something slightly different. So take a look at this situation now. All right, so what we've got here is we have a change. All right, we initially had this plan, we're going to run so far at a certain rate, and it was going to take so much time. And we're going to kind of tinker with the equation here. All right, now instead of running kind of the original distance, if you will, all right, maybe we can just kind of go write that up here, the distance for the original at an original rate, at an original amount of time, we're going to alter some things. We're going to run twice as far. So what we're doing in this equation is we're in effect doubling the distance over here. Okay, I've multiplied the left side of the equation by 2, and rules for equations still apply here. You have doubled the left side of the equation, so we must double the right side of the equation. So that could come from a variety of things. You could increase the rates, increase the time, some combination of that. But in the problem, it says the same originally planned rate. So actually, you cannot adjust the time, or excuse me, adjust the rate, which means the doubling of distance must be mirrored by a doubling in the amount of time it takes. And I think that makes intuitive sense, right? If you want to go twice as far, you've got to take twice as long if you're not going to increase the speed. So this leads to something else that's important, not just for rate distance problems, but also for work problems. And that is when you make a change on one side of the equation, that change is kind of a proportional change on the other side of the equation as well. Cool. All right, we've got someone international. That's awesome. Appreciate you waking up really early or staying up really late to watch this. All right, let's do one more here. So that doubled the time. Ooh, Panama, very cool. That one doubled the time. Let's take a look at something else, another way you could alter some of the stuff in this equation. Right, so again, we kind of had this original plan or kind of the default distance, rate, and time. But now we're going to tinker with that a little bit, okay? So I'll go ahead and maybe this one I'll write out a little bit more down here. So I had a distance, I had a rate, I had a time. I know I'm multiplying these. And I can think about these as kind of based off of the original, all right, or the original plan. Originally planned distance, originally planned amount of time, the planned rate. And what we're doing here is we're going to run the same distance. So I'm not going to change the left side of this equation, but I am changing part of the right side, right? I'm decreasing the amount of time it's going to take. And if you are kind of thinking through this, like say you're going to go for a run, and instead of taking a little bit of time, or instead of taking the normal amount of time, you're going to take less time, and you're still going to cover the same distance. You understand that, oh, you're going to have to increase the speed at which you're running. So what's happening here is the time has shrunk. It's only 80% of the original amount of time, and maybe we should best express that as a fraction. Take a look at what's happened now. I've gone from the original equation, distance equals rate times time, and I've changed the right side. I've multiplied it by 4/5. Now remember, we're going to run the same distance as planned, so you can't change the left side. You've changed the right side here, you can't change the left side, which means you've got to change the right side in such a way that it counters this change. And so if you have multiplied the right side by 4/5 and you want to keep the left side the same, that means you also need to multiply the right side by the factor that's going to counter this factor. And so if you multiply the time by 4/5, you're going to have to multiply the rate by 5/4. Those will then cancel out and give you your original distance. So to run 5/4 of your original rate, well, that's a quarter faster. That's 25% faster. Okay, so again, these changes are proportional, right? If you double the distance, you can either double the time or double the rate, or you could quadruple the rate and half the time, but the product over there has to equal to the factor of 2 on the other side of the equation as well. Okay, so understanding these changes is really, really important, and it's also really important for work problems. Okay, so those are some important things to keep in mind. Let's talk about a few problems and see maybe how some of this stuff plays a role, and also some other best practices to keep in mind as you're going through these problems. All right, I'll give you, a minute and a half, 2 minutes to take a look at this one. All right, we're pushing 1.5 minutes, just so you're aware of your time. All right, I'm going to go ahead and move the answers down a little bit, give us a little bit more room to work. Go ahead and poll in with which answer you chose for this one. I'd like to see kind of where we are with this question. Okay. All right, so we're kind of spread out. That's good. Good for a problem here. All right, cool. I won't tell you what the answer is yet because we are, of course, going to work through this problem. But I think there's a couple stages to working through this problem, okay? Like we read this problem down, we're getting some information about Carlos and how long, in terms of time, it took him to cycle from his house to the library. There's a question about the distance, the actual length, physical length. And okay, so that might have the ingredients of a distance, rate, time problem. But then when you look at the statements, they're about speed. They're about the rate, okay? So this has all the ingredients of a distance, rate, time problem. And because the statements discuss the rate, facts about Carlos's average speed, I think it's a good idea here to get to a version of the question that's about the rate. Okay, so the question really here is about the distance. Was the distance greater than 6 miles? But I want to see if we can make that question about the rate at which he traveled. So that's going to be my job for you guys. All right, we need to take a moment and try to figure out how you can rephrase this question up top as a rate question instead of a distance question. So take a moment to do that. Let's think about this. Suppose the distance he traveled was exactly 6 miles, okay? If he travels exactly 6 miles in half an hour, then what's his rate in miles per hour? 6 miles in half an hour. So if we kind of put that into the equation, 6 miles in half an hour, well, I suppose the rate would have to be 12 miles per hour, and it does, okay? So that would be if he cycled exactly 6 miles. His rate would be exactly 12 miles an hour. The question here is, did he cycle greater than 6 miles? And if I increased the distance over here to something above 6, what that does now is with the half hour anchored, it would increase the rate to something above 12 miles an hour. So one way that you could rephrase this question is something like this. Was his rate greater than 12 miles per hour? Because that's the only way he's going to be able to cycle greater than 6 miles. And the utility of this is such that both of these statements are about the rate. And so now I can kind of communicate from statement to question a little bit better. Okay. So 12 miles per 1 hour is a nice rate. But of course, we saw in one of those sample problems earlier that we need to mind our units, okay? And miles per hour is not the same thing as feet per second. So this is kind of one of those prime unit conversion problems. Let's try to convert 12 miles per hour to some feet per second metric. So I'm going to give a little time for that, and then I'm going to start talking through it. How do you convert miles per hour to feet per second? It's probably one of those annoying conversions that you've done enough times in your life you should have memorized, but it's some really strange number. some strange factor, so it's not worth memorizing. Okay, let's walk through the steps here. My goal is to end up with the numerator of feet and a denominator of seconds. Let me handle the time situation first here, okay? To get rid of hours in the denominator, well, I'm gonna have to include hours somewhere in the numerator. Let me convert hours to minutes first. 1 hour is the same thing as 60 minutes, okay? So literally this fraction, 1 hour over 60 minutes, is 1, okay? I know it looks like a 60th, but that's because the units are changing. But in terms of like actual lengths of time, an hour is 60 minutes. So all you're doing here is multiplying by 1 in a sense. You're just changing the format of the fraction. You're not changing the real value, you're just changing the format, okay? But you're not done. You're not trying to get to minutes, you're trying to get to seconds. So the next factor you need to do is 1 minute is the same as 60 seconds, of course. And what this is going to allow you to do is cancel out the hours and the minutes. And now I've got something that has miles in the numerator and seconds in the denominator. Cool. We took care of the time portion. Now let's similarly take care of the distance portion. And they give you the conversion here. I've got miles in the numerator. I don't want miles in the numerator. I want feet in the numerator. So let's write feet in the numerator here and put the mile in the denominator. 5280 feet is the same as 1 mile. That's going to eliminate the miles. And now what we've got here is 12 times 1 times 1, so just 12, times 5,280 feet per 1 times 60 seconds. So 60 times 60 seconds. We should be able to clean that up a little bit, okay? 12 over 60 is a fifth, so I'm just going to take care of that here. Becomes 1/5. Well, 5,280 and 60, of course, both end in 0, so you can factor out a 10 from both of those. That should go away. And let me just write it down here and clean this up. 1 times 280, or 1 times 528 is still 528 feet per 30 seconds. At this point, I don't think you can, do a lot of good work of simplifying. You're just going to have to do the long division. So let's do that. How many times does 30 go into 528? Well, 30 goes into 52 once. Do some subtraction. Not a really fun way to do this, but it's going to have to happen. And then 30 goes into, well, I know 30 goes into 210 7 times. Subtract there, 18 left over, bring it down. Looks like, okay, so 12 miles an hour is the same as 17.6 feet per second. That's a lot of unit conversion, but again, you'll see, I think in this problem, it's a lot harder to go from miles per hour to feet per second than it was in that, that problem we looked at a few minutes ago. So good to walk through the steps there. And if 12 miles an hour is the same as 17.6 feet per second, I can actually rephrase this question, I'll put it in a different color, to something like this. Hey, was Carlos's rate greater than, not 12 miles an hour, but 17.6 feet per second? And that's kind of the key rephrase here. Yeah, a little time consuming, but this is not an easy problem. This is a tough one. So is the rate greater than 17.6 feet per second? Let's take a look at statement 1. Well, it was greater than 16 feet per second. Well, knowing that it's greater than 16 feet per second is somewhat helpful, but it doesn't help me definitively answer whether he was going faster than 17.6 feet per second, right? There are some values greater than 16 that are greater than 17.6, and there are some values that aren't. So this isn't going to be sufficient enough. Okay, statement 1 isn't sufficient. It's not specific enough information. So statement 1 is not sufficient. So answer A is out, and answer D's got to be out as well. All right, let's take a look at statement 2. The average speed was less than 18 feet per second. I want to know, was it greater than 17.6? Well, again, there's some values that are less than 18 feet per second, like 17.9, 17.8, that indeed are greater than this rate. But there are plenty of rates, 2 feet per second, 0 feet per second, that are less than 17.6. So I'd say this one is also insufficient. It isn't sufficient here. So answer B's got to go. And now we want to see if, knowing that somewhere the rate is between 16 and 18. All right, that's what the statements together tell you. Well, is the rate greater than 17.6? Again, you're not sure, right? I know it's somewhere within this range, but it's not specific enough to tell me, oh yeah, it's in the top quintile of that range. Right? It could be 16.5, it could be 17.8. And so even combined, these two statements are not going to be correct, or not going to be enough information. So the answer here is going to be E. I know this is a hard problem because not many of you picked answer E when I launched the poll. So if you missed it, right, this is a great kind of opportunity to take a look at why you missed the problem. Did you get lost in the conversion? Did you spend kind of too much time converting feet per second, 16 feet per second to, how many miles that would be in half an hour, instead of rephrasing this information to the feet per second up top? Just try to, take a moment and try to figure out which problem or which part of the problem gave you the most difficulty. And that's something you want to work on. The good thing is you can practice this stuff on your own. Like, you can just come up with some rate. 14 miles in 26 minutes. And you should be able to convert that. It might not be a clean number, but you should be able to convert 14 miles in 26 minutes to, yards per minute or something like that through your conversions. Yeah. If you picked C here, right? And, C is not, it's the second best answer, I suppose, because clearly we said A, B, and D are wrong. But, try to figure out, what kind of why C doesn't work. Like, this range between 16 and 18, but, the question is actually more specific than just what the range tells you. All right, good stuff. All right, let's take a look at another problem. Take a look at this one. Give you a little bit more time for this one. All right, let's go ahead and pull in for this one. What you've got for this one. All right. A little more, looks like there's a little more confidence in this one based on how quickly people are pulling in. While this pulls up, I just want to say I've had some questions about estimating on the previous problem. And, you know, estimating I think is a really good tool. It depends, though, how far you're estimating, right? We ended up getting that rate. The question was like, was Carlos's rate 17.6 feet per second? And that seems hyper specific. Like if you ended up estimating that to 17.5, like you're in good shape, right? If you end up estimating that to, you know, 17 point something, you're still in good shape on that problem. But if you end up estimating Carlos's rate to like 20, like was his rate at least 20? Well, then statement 2, which said it was less than 18, you're going to think statement 2 is enough information incorrectly. Or if you estimated, instead of getting 17.5 or 17 point something, you estimated and said like, well, I guess his rate, that's about 15 feet per second. Is he going faster than 15 feet per second? Then you're going to think that statement 1's enough information because it said he was going faster than 16 feet per second. So, you know, with a lot of estimation, it kind of depends on the degree to which you're estimating. And in that case, because the ranges are like 16 to 18, you're going to want to estimate like not too much. I don't know what the best way to say that is. You're going to have to be like pretty good about you know, how detailed you are with those calculations. Cool. All right, the majority of you have this one right, so that's really good. I do want to talk about this problem just as a way of setting up some of your work. So one way to keep track of elements in rate problems is by coming up with the charts, especially when there's either like multiple drivers or runners or travelers moving at once, or when there are multiple parts to a journey, which is what's going on with Susan here, okay? If you don't set up a chart, I think you're going to be tempted to fall into the trap here. And the trap is answer C, okay? I know we talk about the C trap sometimes with data sufficiency. C is a trap here in this problem solving question. And it's because people will see, well, she went 30 miles an hour for, you know, part of her trip, and she went 60 miles an hour for part of her trip. And so the average of those two is 45, and they end up picking C. And you have to be careful here because you haven't considered how long Susan spent at each of those speeds, right? You know, say you are driving somewhere and you go 60 miles an hour for, you know, 99% of the trip, and then 30 miles an hour through the residential neighborhood at the very end. Your overall speed is going to be closer to 60 miles an hour because you spent so much more time, so much like a higher percentage of the trip going at the faster speed. Instead of like, maybe you got on the highway and went 60 miles an hour for like a second and then hit traffic and then had to go 30 miles an hour the rest of the way. Like now your average speed is closer to the slower end because you spent a lot more time going at that slower speed. So I did a weighted average, one of these prep hours a couple months ago. Might be worth checking out if that's confusing at all. But we've got the elements of Susan's trip. We can go ahead and fill in part 1, part 2, and fill in what we know. Okay, well, the first part of her trip was 30 miles. Let's go ahead and put that in here. Hey, the distance is in miles, and I don't think the units are going to be a problem here. The rate was 30 miles an hour. MPH. And so the time it took her must be 1 hour, right? Because 30 times an hour gives you 30 miles. Part 2, faster part of the trip. Well, she's going 60 miles an hour, okay? And that's only going to last for 30 miles. So it should only take half an hour, right? And this is that kind of proportional thing. You've kept the distance the same, you've doubled the rate, so the time gets cut in half. Okay. And so what we've got here, Robert, I got your question. I will try to address it here. What we've got here is you've got a total of 60 miles. You've got a total of 1.5 hours, or we'll just call that 3 halves of an hour. And that should be enough to figure out your rate. Average rate, average speed is always total time, so we'll call it time total. Excuse me, set that up improperly. The total distance over the total time. That's the average or the overall rate. Okay, and so what we've got here is a total distance of 60, a total time of 3/2. 60 divided by 3/2 is the same as 60 times 2/3, which is 120 over 3, which is 40. And 40 makes sense because, well, 40 is closer to 30 than it is to 60, but that makes sense because you spent more time driving slower, right? And that's how you can kind of estimate this. You spent more time going slower, so the slower speed has more weight to it. Okay, it has a higher influence on your overall average rate. So if you chose C here, you want to watch out for those types of average questions, right? Oh, average, I've got two values, I'll just take the average. And that's going to be a very common type of trap, one you should be aware of. Cool. Robert, I hope that answered your question a bit. But that's kind of how you can just use ballpark to kind of figure out, oh, it's not one of these faster ones, because that is much closer to the higher speed average when you were going at that speed for less time than the slower speed. So it's got to be A or B. And if you want more practice with that, go check out the weighted average video I did a few months ago. A lot of questions related to that. Good stuff. All right. You know what? I have one more rate distance problem, but I think I'm going to save that. I might throw it up at the end in case people want a challenging problem. So I'll go ahead and save that. But for now, let me back out of here so I can find the appropriate slide. We're going to take a look at some work-related problems. Let's get this happening. All right, so I think a lot of times people get more stressed out about work-related problems than they do distance problems. But a lot of the mechanics are similar. Okay, a lot of the same best practices. You want to make sure you're minding your units. You want to understand how the changes work when you alter one side of the equation. So let's talk about that equation. The work rate equation is pretty much like the distance traveled equation. In fact, you can think about, the distance you're traveling as work done. Okay, so the amount of work that's completed is equal to the rate at which someone or the machines do the work, multiplied by the time it took to do the work. And that distills into something like this. Some people think of that as W equals RT. Work is equal to the work rate times the amount of time. And same thing with the distance ones, right? If you double the amount of time, you should be able to double the amount of work you do by keeping the rate constant. Or if you double the amount of time and you want to get the same amount of work done, think about that. Now you have twice the time to do the same amount of work. You can slack off a little bit, right? You can cut your work rate in half. So changes are proportional there. So let's think about this one. This is a slightly harder changing problem here, but worth thinking about. All right. Hopefully you've had some time to think about this. All right, so what's happening? Well, painters decided to do more work. All right, I'm going to paint 2.5 times as much as normal. And to accommodate this, well, we're going to slow down the rate. And we got to figure out what's going to happen to the time here. All right, there's a couple ways we can handle this. One way you can handle questions involving, work increases, distance increases is by picking some numbers, right? There aren't any specific numbers associated with the amount of work that the painter was going to get done and now wants to get done. You just have relationships. So this is a great opportunity to just make up some numbers that satisfy this. So let's think. Let's say originally the painter was going to paint. Anyone think of a good number of square feet that's going to kind of be helpful for this problem? All right. Let's say originally the painter, I'm going to make sure I'm on the right window here, was going to paint 10 square feet. Okay. Let's think about what his normal square foot per hour rate would have been. You think about what his normal square rate per hour or square foot per hour would have been. Okay, maybe we could have said he was going to do 5 square feet per hour, and that should allow you to figure out how long it would take. All right, that should take him or her 2 hours. All right, let's alter this now. All right, now let's go to a different color. Now the painter is going to paint 2.5 times as many, or 25 feet squared. But he's only going to paint, or she's going to paint, oh, I guess it is a he. He's going to paint at 5/6 of the normal rate. So I need to know what 5/6 of 5 is. 5/6 of 5? Well, just multiply that out. 5/6 times 5 is equal to 25/6. So we're going to slow it down a little bit. 25/6 feet squared per hour. And now we've got to figure out how long that's going to take. Well, remember this equation. You need to multiply something by 25/6 to get to 25. That's very convenient. Shana and Yvonne, you picked some good numbers. Clearly, you need to multiply by 6 here, 6 hours. 6 hours times 25/6 should equal 25 feet squared, and there we have it. So the time has tripled. Okay, those are some good, specific numbers to figure out what's actually happening here. If you wanted to see it kind of in a more abstract way, you could say, well, the work is being multiplied by 2.5 or 5/2. So you need to multiply the right side of the equation by the same factor. And you can do that a couple of ways. You could just increase the work rate by 150% so that it's now 250% of what originally it was, and the time stays the same. Or you could keep the work rate where it was and increase the time by 5/2, okay, by a factor of 5/2. But actually what the problem says is the work rate's actually going to decrease. So I've multiplied the left side by 5/2. I've multiplied the right side by 5/6. That's not the same, okay? And so you're going to have to multiply the time by something to combine with this factor of 5/6 to get 5/2, and that's the factor of 3 that we came up with. 3 times 5/6 is 5/2, and now you've multiplied both sides of the equation by 5/2. Good. Okay, good stuff here. Let's take a look at a couple more problems here. Good ones. Give you a couple minutes to think through this one. And I'll go ahead and throw up the poll here if you want to poll in. Still got a little time. I'm going to give you another 30 seconds or so. All right, looks like people have a good idea, good handle on this one. All right, go ahead and end it there. Okay, we're going to solve this kind of the textbook way in a second, but I think it's valuable to think about kind of just the general logic behind some of these working together problems, right? Ann and Jordan are teaming up and they're working together and what that means, right? Like, think about this, like they're going to team up and you should assume on these problems that they don't get in each other's way. Like it's going to be a cordial, you know, companionship on this project. And so like, we already know Ann could do the document herself in 2 hours. So even if Jordan and Ann team up and like Jordan falls asleep, like Ann's still going to get the job done in 2 hours. So for that to take 3 hours for them to do the job, that doesn't make sense, right? Same thing for 5 halves, right? Again, Ann could do the job by herself in 2 hours, so it makes no sense for it to take now 2.5 hours for them both to do the job. Okay, so we've gotten rid of both of those. Now, imagine this scenario. Imagine instead of Ann and Jordan working together, you had 2 Anns, like Ann and Ann's clone, right? And they're going to translate the document. Right? Well, you've got 2 identical, I'm going to come back to that question in a second. We've got 2 identical workers, one of whom could have done the job in 2 hours. So now that there's 2 of the workers, you should cut the time it takes in half, right? So even if you had 2 Anns, right, this would get done in an hour. So there's no way you can take Ann and a slower person than Ann and do it in faster than an hour, okay? So 2 of the faster translators wouldn't even get it done in under an hour. So answer A's got to go. And then if you had 2 Anns, you could do it in 1 hour, but you don't have 2 Anns. You've got Jordan, Slowy McGee over here, holding things up. And so it's not going to take only an hour. It's got to take a little bit longer than that. And so you could basically get down to answer C just with some of that, you know, common sense. Question came in, could we eliminate a handful of, I'll tell you in a second, we could eliminate a handful of these answers maybe because, you know, based on the way the answer choices relate to each other. Yeah, I would say A and C are what we call answer pairs, okay? And answer pairs are often, you know, tempting because if one of them is right, you could clearly see how someone ended up with the wrong answer. They just switched things around somewhere in here, okay? Valdez asks 6/5 would be what in minutes? Now we should be able to figure that out, right? 6/5 in minutes would be, yeah, 72 minutes. You should just be able to take, this is, I mean, why not do this? Since this is the time for this, right? If you have 1 hour, or sorry, 6/5 of an hour, and the conversion is to minutes, you would just convert, well, there's 60 minutes in 1 hour. Now the hours cancel, and now you've got 6 times 60, which is 360 over 5, and that's 72, as Daniel said. So I would say in this problem, like A and C kind of stick out to me because, you know, one is we had clones. This is going to be the evil twin of the other one. And oftentimes evil twins are, well, they're evil and they're tempting and they're incorrect. So if one of them's an evil twin, one of them's right. And so maybe you could say, based on the answer choices that are given here, the answer is probably A or C. Another kind of good way at looking at the answer choices and what hints may be hidden there. But I want to talk to you about kind of another way to do this, and it is through a chart. Let's come up with Anne's kind of row of information and then Jordan's row of information. So if we wrote in Anne here and Jordan, we know, well, Anne can do one document, okay, and the time's in hours. So she can do one document in 2 hours, which means her work rate is half a document per hour. Okay. Documents per hour. So her rate is half of a document per hour, and that's why she can get a full one done in 2 hours. Jordan can do one document in 3 hours, and so his work rate is a third of a document per hour. When people work together, when machines work together, all right, when work is being done simultaneously, you want to combine the rates, okay? Add the rates together as long as the units are the same. You cannot add like half a document per hour and 1/20th of a document per minute and hope that that works, okay? Get the work rates the same units and then add them up. So we've got A and J and Jordan, and together they work at 1/2 plus 1/3, 5/6 of a document per hour. Okay, so 5/6 of a document in 1 hour. And that's the tempting thing about 5/6, okay? But they're not asking you how much you can get done in an hour. They're asking you how long it takes to complete the document. And so you don't want 5/6 of the document, you want 6/6 of the document. And so you need to multiply both sides by 6/5 here to get the real amount of time. 6/5 times 1 hour, or just 6/5 of an hour. Or 72 minutes, as we pointed out. Cool. How many seconds is that? Bonus points for that. 4,320 or something like that. All right. Cool. Let me know if you have questions about this in the chat room. Based on some of the answer choices that were submitted on the poll, I think we're feeling pretty good about here. Big thing to take away here is when people are working together, you want to combine their work rates. Okay. But you can also pretty much get to answer choice C just with some common sense. Good to know. All right, got a slightly more difficult problem here. Well, at least I think so. Maybe you feel differently. Go ahead and take some time for this one. All right, I'm gonna go ahead and pop the poll up for you. All right, getting some diversity in the answer selections here. One thing I do like is that no one picked answer C. And answer C is not right. I think answer C is just one of those like silly traps, right? Like, oh, like we've lost 4 days. Clearly we need 4 more machines. Like that doesn't work, right? That logic doesn't hold up. That's too easy and also too wrong. So let's kind of figure out what's going on here, right? We've got this, you know, our work rate equation, right? I'm glad you guys can't see that, what's going on here. All right, work equals the rate times time, okay? And what we've got here is we've got one job, a certain job that gets done, okay? And I just want to see, you know, what's going to take to get the same job done in less time, okay? So the amount of work that's being done total is not changing. Okay, what we are changing is we're changing the number of days, right? We're going from 12 days to 8 days. All right, so I've got a question here. Why doesn't this logic hold? 12 days to 8 days. Ah, that's 25% faster. Hence, you need 25% more machines. So 1.25, 25% more, times 6 gives you 7.5. There's a couple things I think are a little incorrect about that. The first thing is going from 12 days to 8 days is not 25% faster, right? I think going from 12 days to 9 days maybe would be 25% faster. But you're not taking only 3/4 of the time. You're taking actually 8 days instead of 12. So the time is changing by a factor of 2/3, okay? You've multiplied, I should just go in a different color here. So we can kind of keep track of the portions of the problem. So what I'm doing to the time is I'm going from 12 days to 8 days. So I'm cutting the time into 2/3. Now what we have to do is, well, when you multiply the right side by 2/3, that might end up causing the left side to be multiplied by 2/3, but it says we're getting the same job done, so the work on the left side doesn't change. So you've altered the right side here, so you're going to have to alter the right side here in such a way to counteract less time. Okay. And we kind of saw this in the previous problem. Like I said, hey, if you double, if you had 2 ands instead of 1, 2 ands can do the job in half the time, right? Because you would cut the time in half, and so you counter out the dividing by 2 or the cutting in half by multiplying by 2, getting another and. And so we need to do the same thing here, all right? If you cut the time a little bit, factor of 2/3, you need to multiply the rate by 3/2, and that's going to leave everything ultimately unchanged, which is what you want because you're getting the same job done. So now the rate needs to increase by 50%. And this is kind of the other problem with that line of thinking is like I decrease the amount of time by 33 1/3%, but I'm not going to increase the rate by 33 1/3%. I've got to increase the rate by 50%, right? Because that's the way these fractions have to work to cancel each other out, right? If you lose 10% of your money and then you get 10% of the your new amount of money back, you don't end up where you started. So you can't lose 10%, gain 10%, and end up where you start. And here, this kind of shows exactly why. It's also why in one of those previous problems where I said you wanted to, do the run in 80% of the time or 20% faster, you didn't increase your rate by 20%. You increased it by 25%. So a similar thing happening here. Okay. So what does it mean to increase the rate by 3/2? Well, I think a lot of people, based on the answer choices they got, understand that the more machines you have working, the faster the rate. And in a sense, you can think of your rate as like how many machines are working at a time. Okay. So if you had 6 machines working originally, 3/2 of 6 is 9. And so you need 3 more machines. Now, there is another way you can think about this, and I'll just kind of talk through that here, and we'll probably wrap this thing up. Another way to think about it is to create this rate chart, all right? And I prefer to kind of do the proportional changes because the rate chart, you're writing down a lot of stuff and it's easy to get lost. And, the more calculations you're doing, the higher chance of, making a silly mistake, which I am prone to do. But what you can do is start filling this out, and I would fill it out like this, okay? Initially, you've got 12 days, okay? And you've got, I guess, we're getting one job done. Okay. We've got one job to do. Sorry, I'm looking at some questions in chat. We got 12 days to do it, and the work rate is, well, really what's going on is it's the rate of, I don't know what the work rate is, but I'm going to call it the rate of 6 machines, okay, because I've got 6 machines working. Okay. And so what I can start doing here is I can start altering things, okay? Like, let me figure out, like, if I didn't have 6 machines, but if I had only 1 machine in 12 days, well, I have a 1/6 of the workforce. I should get only 1/6 of the job done. Okay. Well, let's think about this. Like, let's keep tinkering with this. Like, if I make the rate of 1 machine, if I keep that, but that machine only works for a single day now, how much work gets done? Well, I would get, 1/12 of this work done because I'm working for 1/12 as long, right? So 1/6 divided by a 12th becomes 1/72 of the job. And I think this makes sense. Like, if a single machine works for 1 day, it gets 1/72 of the job done. And so if you increase the number of machines 6-fold and you increase the number of days by a factor of 12, you multiply by 6 multiplied by 12, that's the same as multiplying by 72, and you can get the whole job done now. Another way of thinking of this is like, imagine you are the employer of these machines, and it's not enough that the machines have taken our jobs, but now the machines want to be paid for their work. And so to get this job done, you have to pay 6 machines 12 days worth of work. That's 72 days worth of wages you're paying out to machines. Now, you could choose to pay those 72 days worth of wages to a single machine that works for 72 days or 72 machines that work for a single day. But it's the same amount of money that you have to pay to get the work done, okay? And that kind of shows it here. 1 machine works for a day. That's 1/72 of the pay you have to make. And now we can start scaling this up, okay? We have, in fact, these machines working for 8 days. So instead of working for 1 day, if you allow the rate of 1 machine to go for 8 days, well, 1/72 times 8 is a 1/9, okay? And so if you let 1 machine go for 8 days, you should get 1/9 of the job done. And then you want to get the whole job done, so you have to multiply by 9. So that would be at the rate of 9 machines for 8 days. Again, like, this is kind of the step-by-step breakdown, but it's a lot easier to see that if you use a 2/3 factor here from 12 to 8, you're going to use a 3/2 factor here to go from 6 to 9 and increase the number of machines by 3 in doing so. Yeah. Okay. Good stuff. Wow, that hour went by so quickly. So what we're going to do is, just for the people who are kind of watching online, and if you want to stick around, I'm going to just go ahead and show a couple more questions. And, feel free to kind of try them on your own or not, if you are satisfied with the work you've put in. So let me go ahead and find those. Here is one of them, okay? And if you're, working at home, watching the recording, I assume you're all pretty much working at home, even the people who are here live. But if you're watching on the recording, why don't you go ahead and pause it here and kind of spend some time to think about this on your own. And after you've unpaused it, I'll just kind of give you a hint. one thing that people will say here is the answer has to be E, because I don't know how long the track is. And if I don't know how long the track is, then I don't know how long it's going to take in time. And without that information, how could I know anything about the average speed? The answer is not E, okay? And in fact, you don't need to know specifically how long the track is and therefore how long it takes, okay? A speed, a rate, a rate is a ratio. And a ratio is a comparison of values. And oftentimes you don't need the specifics of each component in that ratio to answer questions about the kind of comparison between them. Like if I asked you what fraction of the class is boys, and I told you that, a quarter of the class are girls. And you could tell me 3/4 of the class are boys, but I didn't tell you how many boys and girls there were, right? Again, it's a relative amount. Or if I asked you, hey, what's the, what fraction of the class are boys? And I said, the ratio of boys to girls is 3 to 2. You should be able to tell me the fraction that are boys in the class is 3/5. Right? Again, I haven't told you specifically how many boys and girls there are in the class or how many total people there are in the class, but you actually don't need that information to solve. And so that's why you don't need to know the distance of the track here. Now, you could, again, just make a number for the track if that makes things easier. Like just say the track is 60 miles. And then you can compute the times for the first lap and the second lap and the overall average speed from that, okay? And that is kind of guaranteed to show you that both statements together have to be sufficient, okay? Because if I could just pick, 60 miles for the track length, you can figure out all the kind of missing pieces in the chart and compute the average speed. But the answer is not C, right? That's too easy, right? If they tell you specifically like, the average speed is 20 for this lap, the average speed is 120 for this lap, that's actually probably too much information, right? It's pretty clear you can solve from that. So that's going to be the C trap in data sufficiency. Okay. Oh no, my chat box, I can't access it. I'm sorry, I'll see if I can access the chat box in a second. Oh, there it is, okay. Yeah, sorry. So the answer here is not C. I know it seems like it wants to be, but it's not, okay? And so I'm gonna push you to see if, one or even both of the statements would be sufficient on its own. And I think you'll find that if you kind of go with, the lap distance of 60 miles, you'll be able to figure it out. Proving it is also kind of fun. I rarely say like doing the algebra is fun, but I think the algebra for this one is kind of cool if you're willing to go down that path. All right, the other question that I had was, no, we did Ann, we did the machines. This one, and this one's from GMAT Prep software. It's in one of the free practice exams that I think is an interesting one. And I would really recommend that if you're going to do this one, you set up a chart, okay? Set up a chart and figure out some rates of these combinations of pumps. So I'll go ahead and give you time to work on that. If you're working on the recording, go ahead and pause this. And what you'll end up with is a system of equations. You'll get a rate for pumps A and B. You'll get a rate for pumps A and C and a rate for pumps B and C. And you've got 3 rate equations, okay? And you've got 3 variables, A, B, and C, and that should be enough to solve for each of them individually. And you can definitely do that, but I will tell you that there is a shortcut once you get to that point that is a time saver and really kind of nice. So try to hunt for that shortcut once you have the rates of these 3 kind of pairs of pumps. All right. Yeah, I think that's about it for tonight. That's pretty good. Yeah, again, if you are interested in checking out like a free course, just go ahead and get in touch with Student Services or go to this link. Love to see you in an in-person class. Although if you're in Panama or China, probably not going to have in-person classes there too often. But check us out online. Come visit one of our online classes. We'd love to see you there. And then I'll be doing another one of these first week of March 5th. Got some interesting suggestions here, reading comp, critical reasoning. I'll mold those over. And I'm not sure if someone else is doing one of these between now and then, but you should be able to check the free resources link on our site, free prep hour, to see kind of the upcoming session.